We were discussing the common source amplifier, the AC response of the common source amplifier. The model we used for analysis was the common source amplifier being driven from a voltage source with a resistance Rs. The transistor is modeled by the transconductance and the three parasitic capacitances between every pair of terminals. This is CdB, and we have the output conductance of the transistor and any load that you connect to the output of the amplifier. So any explicit capacitive load you connect can be absorbed into CdB also. And the transfer function of this turns out to be a second order function with a right half plane 0. I will call this GL prime, which is the effective load, GL plus GDS. Okay. And this transfer function we approximated to find out, rather we made some approximations to find the poles of this transfer function. The 0 is at plus GM by CGD, and the low frequency pole is at essentially, the low frequency pole turns out to be the source resistance divided by the Miller multiplied CGD plus CGS. Okay. And also, as you can see, as you increase CGD, this will monotonically decrease. As you increase CGD, the very first term in the denominator becomes much more dominant compared to others, and essentially the pole will be inversely proportional to CGD. Okay. And the higher frequency pole P2 is some fraction of GM plus the load resistance that's connected. The load resistance everywhere is the primed total load resistance. Okay. Plus some contribution from the source resistance as well, divided by the total combination of capacitances you see at the output. Okay. And this increases with CGD. And this we will see later will be used for splitting the poles, that is moving one pole to a lower frequency and another to a higher frequency. Okay. That is, we will do that when we want to use this amplifier inside a feedback loop. What is the unity gain frequency of this amplifier? Assuming that P2 is at a very high frequency, beyond the unity gain frequency, what is the unity gain frequency? What's that? Yeah, what is that? That's true. I mean, if it behaves predominantly like a first order system, it's the product of the pole and the DC gain. What is that product? Approximately. We will consider a scenario where CGD is dominant. Okay. Huh? GM by CGD. It says the answer is GM by CGD. Is that correct? So here are this is the pole and the DC gain is GM by GL prime minus, of course. What is the frequency at which the gain magnitude becomes unity? What's that? Let's assume that CGD is very dominant. GS by CGD. Is that correct? If the transfer function behaves predominantly like a first order system, then it's the product of DC gain and the first pole. Is this part clear to everyone? If we have a certain DC gain and then beyond the unity gain frequency there are some poles and the dominant pole is here. Okay. And this is falling off at minus 20 dB per decade or essentially inversely proportional to frequency. Okay. So what is this point? This is equal to ADC times P1. Is this part okay? And what is that value for this transfer function? So ADC times P1 is GM by GL prime, GS by this plus CGS plus CDB times GS by GL prime, which turns out to be okay. Now, let's assume that CGD is not very small. Obviously, if CGD is 0, then CGD, I mean, it doesn't come into picture. But if CGD is moderately large, first of all, we can perhaps neglect GL prime by GL, GL prime by GM, and GS by GM in comparison to 1. Okay. And similarly, GL prime by GM times CGS can be neglected in comparison to CGD. Okay, that's the assumption. So this also goes away. And GS by GM times CDB also goes away in comparison to CDB. So if CGD, CGS and CDB are of the same order, then only this term remains. Is this part clear? If all three capacitances are of the same order, these two are multiplied by some numbers significantly smaller than 1. Is that okay? So the unity gain frequency approximately is ADC times P1, which turns out to be GS by CGD. Okay? Huh? Yeah, that's correct. Not necessarily. We are no, not necessarily. Why do you say that? If it's driven from another amplifier, it's the output resistance of that amplifier. So it's not necessarily low. And in fact, for now, since we don't know any other type of amplifier, we can assume that it's driven from another common source. So it's of the order of the GDS of that amplifier. Okay. So this is true under many assumptions. That is, CGD, CGS, CDB are of the same order of magnitude, and also that GM by GS and GM by the effective load are much more than 1. Is it clear how the answer was derived? The product of the DC gain and the first pole turns out to be approximately GS by CGD. So it's independent of the GM of the transistor or anything of the sort. It depends only on the source resistance and the coupling capacitor across the amplifier. Does this result make sense? Why do we get this? Why do we get GS by CGD? How come the whole thing becomes independent of GM and everything else? Yeah, why is that? Have you seen other circuits in which this happens? All the pardon? All the signal is? Okay. Then the gain will be 0, right? Or 1. So what is the, I didn't understand. Why does the unity gain frequency come out to be this? It is true, like when you say all signal is passing through CGD, what do you mean by all of the signals? What's that? Feedback. There is feedback, yeah. Same with what? When the closed loop gain equals 1? Yeah, that's correct. So what was it you said earlier? At this frequency, the feedback fraction is 1. That's not, yeah, that doesn't directly say that that's the unity gain frequency. In fact, if you look at the feedback fraction, that's 1 over square root of 2, right? The magnitude of it. Have you seen a circuit like this where you have some resistor and some capacitor, and it behaves like it behaves like some block with a unity gain frequency of GS by CGD? What would you have here? Huh? Op amp. So what is the frequency response of this block if it's an ideal op amp? What's that? Integrator. It is just GS by S times CGD. And the unity gain frequency of that is GS by CGD. So something like this is happening in our amplifier also. That is, we also know that this is more or less true if the op amp is non-ideal, meaning if it has finite gain and so on. Okay. If the op amp has finite gain, then the integrator itself has a finite DC gain. It does not have infinite DC gain. That's what happens. So, okay. Why does the op-amp give you this transfer function? Why does the ideal op-amp give you this transfer function? What is the definition of the ideal op-amp? Huh? Yeah, so the input node has very little incremental voltage. Okay, that is, this is incrementally grounded. So this means that the current will be Vi times Gs and all of it flows through CGD. Okay, that's the action of the op-amp. Now, under the assumptions we made, the transistor, the single transistor also behaves similarly. Okay, what did we say? We said that the high frequency pole is at very high frequencies and that the DC gain is significantly large. Okay, so what does it mean? For if you take any particular value of output voltage, okay, or any incremental current in the transistor, the incremental voltage at the gate source is rather small. Okay, all the approximations we made, neglecting GL by GM and GS by GM in comparison to 1, that's what this means, right? That the incremental voltage of the input is very small. So this behaves like a virtual short, and the op-amp, the amplifier behaves like an integrator with a unity gain frequency of GS by CGD. It's only an approximation, but it's a good way to remember what's happening here. Okay. Of course, this is true only when CGD is significant. If CGD is very small, obviously it's nothing like an integrator. Is this okay? So, you have an amplifier. Okay. So let's say this is all the circuit we have. So there is a certain current flowing here, which is I. Okay, and that comes from the transistor. In this case, I am assuming that this is open circuited. Okay. Let's say all of this current comes from the transistor. So what will be the voltage here? What will be the voltage here? Huh? Constant. Why? No, this is some I. If this is I, what is the voltage here at this? What is this current? I. So what is this I by Gm? Okay. So if I by Gm happens to be very small, then I will approximate it to 0. That's what is happening, right? So if the transconductance of the transistor is very large, then you need very small incremental voltage at the gate source to get any increment in the drain current. Okay. So if the transconductance of the transistor is very large, then the incremental gate source voltage is very small. So it can be assumed to be a virtual ground. Exactly what happens in an op-amp or in any high gain feedback network. Okay. So here you can also think of this as a forward amplifier without CGD, and CGD as being connected in feedback. Okay. If the gain of the forward amplifier is very large, the gain is independent of the forward amplifier's gain. Okay. So this behaves approximately like an integrator whose unity gain frequency is GS by CGD. So we will come back to this repeatedly when we design feedback amplifiers around these transistors. Okay. So what we did so far was we analyzed the common source amplifier, and the transfer function is some complicated function of the parasitics. Now it's hard to analyze it as it is. So we assume that some terms are significant in some cases and insignificant in other cases. So if CGD happens to be significant, then you will have pole splitting. Essentially, you start from very small values of CGD. You will have two poles at let's say you start with 0 CGD, the poles will be at GS by CGS and GL by CDB. Okay. And as you introduce CGD, this moves to higher frequencies and this moves to lower frequencies. When I say this, I mean the pole associated with GS, and here the pole associated with the output side. Okay. Now once that has happened to a sufficient degree, perhaps you start off with a transfer function like this, then for a particular value of CGD, the transfer function becomes something of this sort. Okay, so it is predominantly a first order system. Once that happens, the unity gain frequency of that amplifier turns out to be GS by CGD. Now the unity gain frequency is of interest because if we do use this in a feedback network, that determines the speed of the amplifier. Is it okay? So, and you can intuitively see that this is GS by CGD by thinking of the transistor itself as the forward amplifier in a feedback loop and CGD being the feedback element. Okay. So, if you do have a situation like this and this is placed in yet another feedback network, and you have to change the value of unity gain frequency, what will you do? So, you will effectively have to manipulate either GS or CGD. Okay. Of course, when you do that manipulation, you still have to make sure that the unity gain frequency is below the second pole. Okay. How much below it is depends on the response you want. If you want a heavily overdamped response or slightly peaky response. Okay. Certainly, you don't want a very a response with a lot of ringing. So, you will not make the unity gain frequency more than the second pole, but you will make it less. How much less you make is up to you. We have already worked out examples of this kind, where if you make it to be half of the second pole, you will get a Butterworth type of response. Okay. So, this already tells you that if you try to use this in an amplifier, you can modify the value of CGD. When I say CGD, obviously here I don't mean the intrinsic capacitance of the transistor. It is the capacitance that you add in addition to whatever the capacitance the transistor has. So, you can view this in two ways. If you think of it as an open loop amplifier, you are not really concerned with feedback, then ideally you would have got a DC gain of GM by GL. Okay. You would have got a gain of GM by GL. Now, because of all these parasitics, you will have some values of poles and zeros. So, the analysis lets you know which is responsible for what, which capacitance gives you what kind of pole. Or you can think of it as some sort of design exercise where you manipulate the values of different components to get the response you want. And in particular, the response we want is that of a first order type of system which helps us make feedback amplifiers. If we do that, then we can manipulate the value of CGD to get the desired unity gain frequency. Okay. And also perhaps to stabilize it. We know that if we start with this black response and put it in a feedback loop, it will be unstable or it will ring a lot. So, we will try to manipulate it so that it becomes something like this. Okay. Yeah, that's correct. The zero also moves. So, we will have to take that effect into account. We will see how to combat that later. Okay. So, that's true. I mean, it's not only the pole that moves, the zero also moves. But we will see how to, first of all, we can analyze the effect of it and see whether it is harmful or not. And what do you think it will do? If we use this amplifier in a feedback network, is the presence of zero good or bad? Is it good or bad? How many vote for good? Bad. Unanimously. Why? This is a right half plane zero. So, we cannot really use it to cancel the pole. Okay. The poles will all be in the left half plane. That's correct. Yeah, we'll come to that soon. Okay. So, we can have other techniques where either the zero goes away or we can move it to other frequencies. But if the zero is there, it is not a good thing because this is a right half plane zero, which tends to give you extra phase lag. Or as we saw earlier in the course, If you have an ideal integrator, the time domain response will be like this. If you have a right half plane 0, what happens? It jumps down and goes back like this, right? So essentially, if this was the element that was giving you feedback, effectively the feedback is delayed, right? In fact, initially the feedback is in the opposite direction to what you want, and it goes back. So effectively, you can think of it as either delayed or being in the opposite direction. So it can trend to instability. Okay. Now, one thing that we have sort of repeatedly discussed is, or discussed meaning repeatedly come to, is the concept of Miller effect. Now, we calculate the first pole with the, firstly let's outline Miller's theorem. If you have an amplifier of gain, I will make it deliberately a negative gain, minus A. And you have a certain coupling capacitor across the amplifier. If the voltage at the input is Vi, the voltage at the output will be minus A times Vi. Okay. So the current through the capacitor is Vi times A plus 1 times SCC. So this current is being drawn out of the input node and being pushed into the output node. Is that clear? So exactly the same current will be drawn out of the input node if you have A plus 1 times Cc here. Okay. So this current will be Vi times A plus 1 times SCC. And to keep the action of the circuit the same, I should not change the current that's being drawn from the output node. For that, I'll add 1 by 8 plus 1 times Cc to the output node. Okay. Now, because the output voltage is minus A times Vi, what is the current flowing in the output capacitor? It's exactly what we had in the original circuit. It is the current in the capacitor is being pushed into the output node of the amplifier, and that is Vi times A plus 1 times SCC. Okay. So in that sense, the two are equivalent, and it is correct, it looks like, isn't it? So we have not changed the amount of current that's drawn from the input node and the output node. So, for instance, let's say I drive this amplifier with a source whose resistance is Rs. Where will the pole be? One by Rs Cc into A plus 1. Is that correct? So in fact, if you evaluate it, it turns out to be correct. The pole will be at minus 1 by Rs Cc times A plus 1. And in fact, in this particular case, it's trivial to see that the answer is the same. I have a first order filter formed by this resistance and this capacitance. So the pole is the same. Okay. So it appears that I can use this theorem to simplify my circuit. Now let me do the same with the common source amplifier. Now I'll replace CGD with capacitance at the input. What will be the value of the capacitance? What's that? CGD times Gm by GL prime plus 1. Okay. I do the same on the output side. What is its value? Okay. So this is what I get, isn't it? So what happens if I analyze what's the order of this circuit? Second order. Okay. But will I get the same answer as, The 0 is not there, and what happens to the poles? Are they in the right place? So I calculated a 0, a low frequency pole and a high frequency pole for this circuit. Okay. Already from this I can see by inspection that 0 is not there. What about the low frequency pole? Is it at the same place here as it's here? Move to the left. Is it roughly the same or not same at all? What was the low frequency pole in this case? In the original circuit? Low frequency pole is the same. It's approximately the same. So the low frequency pole was minus Gm by CGD, Gm by GL prime plus this, plus CGS, plus, okay. And if I calculate it from the bottom circuit, I will get everything except these two terms, right? So, and those terms seem to be somewhat insignificant, so perhaps I can ignore them. Is that okay? Is it clear that if I calculate the pole from the lower circuit, I will get this part except the highlighted ones? So I get, So I have a first order low pass filter here with GS. What is the pole in this part of the circuit? GS and this capacitance. GS divided by the total capacitance that you see, right? It's the first order. So GS divided by this, which is one of them, and this, which is the other one. Okay. And the highlighted parts, perhaps, maybe let's assume that they are insignificant. So perhaps we can get the right answer in some situation. Is this okay or no? If Gm by GL is very significant, then that's the dominant part, so we don't have to worry about other things. What about the output pole? The pole, I mean basically the pole P2. Is it the same in the two cases? Yeah, so actually if you do calculate the pole from this, it will be related to GL and CDV and CGD. Okay, it's not so much dependent on GM. Whereas in the real analysis, we saw that it is predominantly determined by GM. And why does this happen? So the analysis we do here is exactly right if we replace this A by A of S. Okay. This substitution will give you exactly the right answer because all the node equations remain the same. So if I write Kirchhoff's current law here, with this A replaced by the appropriate frequency dependent gain, it remains exactly the same. But then the whole point of the Miller approximation is lost, because there the idea is you simplify your circuit somehow and use real capacitors. Now to determine A of S, you have to do the whole analysis again. So, but the low frequency gain, the low frequency pole has the correct value, because at that pole the gain of the circuit has not started falling off. Okay. So at near P1, A of S is approximately equal to Gm by GL prime. Okay. But at the high frequency, near the high frequency pole, A of S has significantly changed, and in this case it's affected by CDB also and by everything else. So you can't use that approximation very well. Okay. But if you do have a broadband amplifier where you have a very small amount of CGD, then perhaps you can use it without too much error. Okay. So this is quite useful for, let's say you have a digital inverter, okay, which is sort of broadband, and you have a small overlap capacitance between the two. So in that case, you can divide it into some capacitance on the input side, some on the output side, and calculate the time constants. You will be more or less okay. Whereas in this case, when we consider CGD to be dominant, at the high frequency pole, the gain has fallen off so much that it doesn't make any sense to calculate it. Okay. Is this clear? So this is why you can't use Miller's theorem to calculate the output pole. And if you do use the exact value of A of S, by definition you will get the same response, including the 0. Okay. But then that procedure is more complicated than trying to use straightforward circuit analysis to calculate the frequency response. So we don't use that. But if you do have a case where you are sure that the pole occurs when the gain is close to the DC gain, then you can use the DC gain value in the calculations. Okay. It turns out to be the case for the input pole. Is this okay? Any other questions on the common source amplifier or the Miller effect? So the bottom line is the common source amplifier gives you a second order response with a 0, with a right half plane 0, and the right half plane 0 part is also significant. The fact that it's in right half plane 0 is significant when you want to use it in feedback systems. Okay. And the poles can be split by increasing the value of CGD. So that's a method for compensation that we'll use afterwards. Okay. Yeah.
So at the unity gain frequency, the output voltage is equal to the input.
Yeah.
So that shouldn't be any current flow through the RC.
No. So at the question is, at the unity gain frequency, the output voltage equals the input voltage. So there is no current through the capacitor or current through RC. Is that correct? So they are not in the same phase, right? So this is 90 degrees away from that. So there will be a current flow through that. Okay. So the answer is that if this is like 1 volt, this is 1 volt and plus 90 degrees. Okay. So the current here will be in same phase as the voltage at the input, and so is this current. It's the same current, and the voltage here will be 90 degrees lagging with respect to that. The output voltage is the voltage measured the other way, so it is 90 degrees leading with respect to the input voltage. Okay. So like with this basic analysis, we can move on to other types of amplifiers and see how they behave, and then later try to put them all together. Okay. And it turns out that in some cases the other kinds of amplifiers will be better, and in some cases you will use a combination of different types. So one of the things I mentioned was that you have a right half plane 0 here, and that can be problematic, assuming that you use it in a feedback loop. Otherwise maybe not, but if you do use it in a feedback loop, you will have a problem. Okay. So any thoughts on how you will get rid of the 0 or change the value of the 0, move it into the left half plane? How might you do that? So here, let me take a very simplified model of the common source amplifier where I will omit everything else, okay, all the other capacitors also. What will be V0? What is V0 in this case? I mean, this corresponds to the gate, drain and source of the MOS transistor. It is the common source amplifier. I have removed all the load resistance, source resistance and capacitance and input. So the current here is GM. So that current flows through the capacitor. Okay. This is CGD. So what is the voltage across the capacitor? GM times VI by SCGD. What is the output voltage? Is this clear? So all of the current through the GM flows through the capacitor, and the output voltage is the input voltage like this minus the voltage across the capacitor. Okay. So this is a very artificial case where I have removed all of the other elements. That's why we get an answer like this where we have only a 0 and no poles. But that's okay. Now this pole, where is the 0? Sorry, there is no pole. Where is the 0? Yeah, actually there is a pole here which is at unity. Maybe I should change this to ideal integrator times 1 minus S CGD by GM. Okay. So there is a pole at the origin and a 0 at plus GM by CGD. Any thoughts on how you will get rid of the 0? If I wanted to eliminate the 0, what should I do? I mean, just look at the equations, like which term should I get rid of here? Which one? This whole thing? Remove? Remove VI. So I have VI minus VI GM by SCGD. If I didn't have this, I would just have the integrator. Okay? Is there some way I can do that? Is the problem clear? I have some bare bones version of a common source amplifier. Very artificial, but works for now. Okay? I have removed capacitances and resistances from the source and the load side. I keep only the elements that give me the right half plane 0 in the first place, which is the transconductor and the feed forward capacitor or the CGD. Now that gives me a 0. Now I set up the equation, the output voltage is input minus this. Just by looking at the equation, I can see that it's because of this that I get the 0. Of course, if I get rid of this also, I get rid of the 0, but then there is no amplifier either. Okay. So I want to keep the amplifier but get rid of the 0. What do I do? What's that?
We are getting a 0 at GM over CGD.
Yeah.
So somehow at that frequency, we remove the VI by putting some inductor. We can
So, in the equation, I have to somehow get rid of the first term. Is that possible? What this equation is saying is that the output voltage is the input voltage plus the capacitor minus the capacitor voltage. So I have to keep the capacitor voltage but get rid of the input. How can I do that? Huh? Series resistor. Where? Okay. One solution is that you have to put a series resistor with the capacitor. What were you saying? You don't give the input directly to the. Instead of V0, take V0 plus Vi. I mean, somehow I take the output across these two terminals. Okay, so that is also possible. So the first thing he said was, what is that? That is equivalent to, you add some term to this, okay, which is equal to minus Vi, right? So that's one of the ideas. I have the output to be the input plus some drop. Maybe I'll add another drop which is in opposite phase to Vi. Is that possible? No, I mean, first let's look at not whether it's sensitive or not, whether it works. The idea he is proposing essentially is that I have the output to be the input plus capacitor voltage. I mean, I have two terms in the output value. Then I'll add a third term which will cancel off the term that I don't need. Is that possible or not? No, I mean the term that I don't need is this, not the other one. Okay. In this particular case. I can't get rid of CGD, right? I mean, obviously that's a trivial solution to getting rid of the zero and the pole and everything. But I want to add another term to this whole set so that I get minus Vi. Can I do that? Can we interchange that? Pardon? You will apply the input here and take the output still at the same place. Is that? Let's assume that that's not possible for now. Okay. Yeah, that what you say works, but it will have some other shortcomings that. Okay. See, the first idea was that Vi minus this is the output. Okay. Okay. So let's say I want to have minus Vi here. That is somewhere in this loop I need to have minus Vi. What do I do? Unity gain where? I mean, that will, I think what you describe will do the function, but that's not following this principle. So we'll discuss that soon. Okay. So if I want to get minus Vi, I need to have another element here. I don't know what it is, which will give me a drop of Vi, right? Instead of Vi minus Vi Gm by SCGD, which is across the capacitor, I will try to get Vi minus Vi times Gm by SCGD. Is this okay? So I want to get Vi minus, I have Vi minus this whole thing, okay? And I want to get rid of Vi. So I want to introduce another voltage drop here. So what should this, what should that thing be? It's a resistance of value 1 by Gm, okay? Because the current flowing here is Gm times Vi, okay? And the voltage drop across this will be Vi. So if you do that, this is GM, the output will be minus VI GM by SCGD. Yeah, so you can investigate what happens if so this has to be exactly equal to 1 over GM to get rid of the 0. So you figure out what happens if the resistance is not exactly equal to this. Okay. So this is one way to do it, and here the idea is that initially we were getting VI plus the term across CGD. Now I want to get rid of the VI term, so I introduce another drop in series with VI. I mean, this is how you come up with circuits. I mean, this is some vague analysis of a bare bone circuit that does not represent a real common source amplifier. But you analyze this, and then the other interesting thing is you see what happens if I connect all of the stuff. Okay. You do the full analysis, including, let's say, the output load. Okay. For simplicity, you just first put one element, just the output load, and then see what happens. Okay. What else can you do? Yeah, think about other ways of, the idea is the same always. Somehow you have this set of equations, maybe you get rid of some term or something of the sort. Okay. The current through the capacitor, the current through the transconductor depends on? Yeah, so that is actually a good point, that if this is the intrinsic CGD of the transistor, the whole thing doesn't work, right? If it's only some additional capacitance that I've added, it will work. Because see, if I have a transistor, it has some CGD, and I can't remove the CGD or lift one of its terminals or anything like that. But if I have a capacitor that is deliberately added across the device, then that can be, the 0 because of that can be got rid of by having a resistor. Okay, so actually I should probably change my terminology. This does not refer to the intrinsic CGD. If you could put a resistor in series with that, that also works. Mathematically the technique works, but in reality you can't do anything to the intrinsic capacitance, or that's the meaning of the intrinsic capacitance. Okay. So if you have placed an additional capacitance for whatever reason, then you will get a 0. And as you increase the capacitance, the 0 will move to lower frequencies. But you can get rid of the effect by adding a series resistor. Okay. So one thing you can do over the weekend is perhaps you add a load resistance or a source resistance and find the full transfer function and then see whether the result makes sense or not.